So next we'll talk about the idea of continuous functions. So that's why this section is called continuity. Now this is an idea that's probably somewhat familiar to you already, but we're going to come at it from a different angle. If I asked a first-year student how to tell if the graph of a function is continuous, I would typically expect a response that's something like the following. You take the point of your pen and touch it to one end of the graph, and then you trace the entire graph. And if you can successfully do that without lifting your pen off the page, then the graph is continuous. Okay, that's typically what I would expect a first-year student to say. And that's correct, but it's not the whole story. Okay, and in fact, the truth is more technical than that, and that's what we're going to get into in this section. So let's start with the definition of continuity at a point. So this definition is, we'll start with a function f. So function f is continuous at the point x equals a if this equation is true. So we're actually going to phrase this in terms of limits. So first I'm going to state the definition, and then we're going to look at where this definition comes from in just a moment. So the definition is this. The limit as x approaches a of the function f of x has got to equal f of a. So in other words, as x approaches a, the values of f of x get closer and closer to f of a. So that's just what it means for a function f to be continuous at a point x equals a. Now, why do we use this as the definition? Okay, well, you can see in this picture, here's a function. It's defined. It's a graph of a function. I could say, well, I won't add any more to this picture because right now because I want to write some things down here in a moment, so I don't want to actually add any more up here. But you can see that the function is defined at a, right? Because there's a solid dot on the graph directly above a. So whatever the y value of this point is, maybe it's right here. I won't label it, but there is a y value to this point. That's going to be f of a. So a is definitely in the domain. Now, is this function continuous at x equals a? Probably not. Like, not the way I've drawn it, right? It certainly doesn't look that way, and certainly not based on the vague definition that I started out with in the intro screen, right? If I try to trace the graph, I have to jump here and jump again to keep on tracing. So that doesn't feel very continuous, and in fact, it's not the way I've drawn it. So let's actually write down the coordinates of all three of these points, even the empty ones, even the ones that aren't part of the graph. So I'll show you what I mean by that. So for this point up here, the x coordinate is a, and what's the y value of this coordinate? Well, it's whatever the y values of these functions, or these points on the graph are approaching, right? So this point is actually a, and then the limit as x approaches a from the left of f of x. Okay, so that is the coordinates, or that is this point written in terms of its two coordinates. Now, what about this point here? Well, that one's a little bit easier because it's actually on the graph of the function. So the x coordinate is also a, but the y coordinate now is f of a. Oop, I need one more bracket to close that point. And then this point down here, again, the x coordinate is a. Now, but the y coordinate is whatever the limit of the function is as x approaches a from the right. So we can write this. It's got an x coordinate of a, and the y coordinate is the limit as x approaches a from the right of f of x. Okay, so that is all three of these points just written down in terms of their coordinates. Okay, well, what would we have to do in order for the graph to be continuous at the point A? You probably expect that all three of these things would need to be connected somehow, right? It's like we would need to, let me add a comment over here. In order to be continuous at x equals a, we need the following. And I'm just going to draw an arrow to some behavior I'm going to do up here, some action that I'm going to kind of try to illustrate in green here. Okay, so basically you need to take this point here and you need to pull it down here and basically glue it to this point. And then you need to take this down here and you need to pull it up here and glue it to that point. That's really that would make this continuous at A, right? You essentially need this. you'd need to rewrite the function so it actually connected there on that dot. And really what that would amount to is you would need this point, and this point all to be the same point. Well, their x-coordinates are already all the same value, right? All the x-coordinates are a. But the y-coordinates are at least symbolically different, right? So what would it mean for all three of those y-coordinates to be equal? And actually that's what we're going to write down here. So for f to be continuous at x equals a, we must have the limit as x approaches a from the left of f of x. That's also got to be equal to the y-coordinate of this point, which is f of a. And then it's these two values have to be equal to now to this y-coordinate, which is the limit as x approaches a from the right. Right? All three of those quantities have to be equal. Now, what does it mean if this quantity here on the left and this quantity here on the right are equal? Right? If this is equal to this, that means the limit from the left is equal to the limit from the right, which means that the two-sided limit, which we've written up here, would exist and is equal to that common value. So the point of that is that this is actually just a more condensed way to write this. Right? So this is actually just basically breaking this down and expanding upon it to make it more laid out. And actually, you know what? I like this way to write it better. This is the most concise way, and it's absolutely correct. But I like this better because it makes me think of this picture. And this picture is a good thing to keep in mind when you're thinking about what it means for a function to be continuous at a point. And typically, if you're investigating continuity at a certain point with a given function, what your standard approach is going to be to calculate all three of these quantities. So if you think of the definition of continuous, if you think of the definition of continuous to be that this equation is satisfied, or this pair of equations is satisfied, that all three of these quantities need to be equal, then you're more likely to just automatically remember what your first step is. So I highly recommend just thinking of this relationship as the definition of continuity. It's just the claim that these three quantities all have to be the same. Okay, so that's what it means to be continuous at a point. What about if we just say something like a function is continuous, but I don't specify a point? Well, you can do that, but it means something a little bit different, so which we're going to specify now. So a function is continuous. So this is a different definition, actually. A function f is continuous if it is continuous at every point in its domain. So in other words, if it satisfies this definition for every single value of a in its domain. Right? If that's true, then you've got yourself a function that's continuous. And if someone tells you that they've got a function that's continuous, what they're really telling you is that it's continuous at each point in its domain. And a lot of functions have that property, that they're continuous at every point in the domain. So here's a list. Not a full list, of course, but this is a list of the ones you'll commonly see that are continuous at every point in the domain. So any polynomial. They're defined at every point in the real line, and so they're defined on R, on all of the real line, and they're continuous at every point in their domains, which is the real line. So polynomials are continuous at every real number, is a better way to say it. Okay, rational functions are also continuous on their domains. Right? Their domains might not be all real numbers because, remember, rational functions are fractions of polynomials. So if their denominators are 0, then they won't be defined. So rational functions, you still have to watch out for domains, but they are guaranteed to be continuous at every point in their domains. Trigonometric functions are continuous at every point in the domains. Right? Sine and cos are defined everywhere, so they're continuous everywhere. Tan, you have to watch out because there's vertical asymptotes at pi over 2, and similarly at pi over 2 plus any multiple of pi. So there's places where tan is not defined, but everywhere it is defined, it's going to be continuous at each of those points. So trigonometric functions, sine, cos, tan, cosecant, secant, and cotan, they're all continuous on their entire domains. Exponential and logarithmic functions. Exponential functions are defined for all real numbers. Logarithmic functions are defined for all positive numbers, but in either case, they're guaranteed to be continuous on their domains. Any radical function. So that it includes square roots, cube roots, fourth roots, and any root you might ever like to consider. Those functions are continuous on their domains. Right? And then at the end, you can see I've added this as well as any composition of functions of these types. So basically, think of it this way: any function you can build from functions of these types. So if you take a polynomial and add it to a rational, and then maybe you compose that with a trigonometric function and divide the whole thing by an exponential function. I'm just saying that as an example, trying to be convoluted on purpose. But any function you can build, no matter how complicated it is, if you built it from functions in these families, then the result, the function that you build in doing that is guaranteed to be continuous on its domain. So let's look at an example of what I mean by that. So the function f, which here you've got a function, it's a composition of several functions. You've got a cube root, you've got sine, you've got a squared function, you've got the addition by pi, you've got a whole bunch of functions composed together, all of which come from this list. So this is guaranteed to be continuous because it's built from continuous functions, right? X squared plus pi, that's a polynomial, right? Sine, that's a trigonometric function. Cube root, that's a radical function. So it's a function that's built from functions in this list, so that's how you know it's continuous. I don't have to do any work to justify that, right? At least if you'll at least agree that to take my word for it about functions in this list, that they're continuous on their domains. Okay, and why is it useful to know that a function is continuous? Well, if you know that a function is continuous at every point in its domain, then that means evaluating limits of the function as x gets close to some value is just as simple as plugging in the value. It's your dream come true. It makes taking limits so much easier, right? You don't have to do complicated investigations. It just comes down to evaluating the function at a single point. So if you're asked to find the limit of a function that is continuous at the very point at which you are approaching, so in other words, if you're continuous at this point in particular, you could just plug that value right into the function. It's wonderful. No, I got a fly going by here. Let's look at an example of that. Okay, so let's say I want to compute the limit as x goes to 0 of sine of x over x squared plus pi. Okay, I have a fraction. The numerator is a trig function, right? Sine of x. So sine of x is a continuous function because it's a trigonometric function. X squared plus pi, that's a polynomial. And if I divide them, I form a fraction between the two. Well, that's a function that I'm building from sine of x and x squared plus pi. So it's a function that I've built from two functions that I know are continuous. So in other words, this fraction is guaranteed to be continuous on its entire domain. So that means if 0 happens to be in its domain, then it's continuous at 0, which means this limit is just going to be whatever you get if you plug 0 into this function. So it makes this great. If you were just to look at a limit like this, it might be easy to fall into the temptation of just thinking it might be hard, right? It looks like it's got, well, you got a fraction, you got sine. A lot of people get intimidated by trig. It might look like a limit that's going to take a lot of work to solve, but it actually isn't. You can just plug in 0. So to actually take this limit, all I have to do is plug in 0. So I get sine of 0 over 0 squared plus pi. Well, sine of 0 is just 0. So I have 0 over pi, which is just 0. I actually originally had this as a 2 in the notes, but I changed it probably because I was thinking of this and I put the pi there by accident, but that's okay. We can just go with this as the example. It's the same idea. So this actually is another reason why. Remember in the previous section I mentioned a few times that we should always get in the habit of whenever you're starting a limit problem, just ask yourself, what would happen if I plugged in the value? Does it work? Do I get a 0 over 0 type? That's something that doesn't make sense, or do I actually get a concrete value? And this is kind of why. If the function you're dealing with is continuous and you plug that value in and it works and gives you a sensible value, well, guess what? You're done. Which is awesome, right? So you don't want to miss that by forgetting to just try to plug in the value. Let's do one more example. This is another example of a function that might look like it's going to be difficult to evaluate, but it really isn't. Okay, so the limit as x goes to 0 of cosine of sine of x. Now that looks a little bit weird. That's two trig functions composed with each other. So they're not multiplied. They're actually one function, sine of x, is plugged into cosine completely. So it's sine and it's cosine composed with sine, right? It's cosine of sine of x. So that's quite a lot going on there. That's a bit of a complicated function, but it's a composition of two trig functions, and trig functions are continuous in their domains. So that means if this function is defined at 0, this limit is just, you can calculate it by just plugging in 0. So let's just see what happens. Cosine of sine of 0. Well, sine of 0 is 0, so this is cosine of 0, which is 1. So we got a sensible value. That's great. That means we got this. And if you didn't get a sensible value, if you got something like 0 over 0, you'd have to just stop and say, okay, that doesn't make sense. That's inconclusive, and you'd have to start over and try something else. And that's going to happen sometimes. Limits can be challenging. Sometimes the first thing you try doesn't always work. But the first thing you should try, at least even if you don't write it down and you just run through it in your head mentally, I know I've said this before, but I'm going to say it again, is just run through the process of plugging in the value. Ask yourself, what would happen if you plugged in the value, right? In this case, it was 0. What would happen? Just ask yourself that. And if you get 0 over 0 or something like that, then you know you have to try something else. But always ask yourself before you start a problem, because it could save you time.